All right, let's take a trip. A trip way, way back in time. I'm talking over 13 billion years, to the very first, most intense moment of creation. We're going to try and crack the cosmic code of the universe's first microsecond. So what did it actually look like back then? You know, before there were stars, before galaxies, before even a single atom could hold itself together. What was the universe made of in that first fleeting instant? It's one of the most fundamental questions you can ask.
And the answer is just incredible. It wasn't a gas, it wasn't a solid, it was a perfect, seamless liquid. And get this, it was hundreds of thousands of times hotter than the very core of our sun, a state of matter so extreme it just hasn't existed naturally for 13.8 billion years.
So what do physicists call this stuff? It's known as the Quark-Gluon Plasma. The best way to think about it is as the universe's original primordial soup. See, today, the fundamental particles that make you and me, quarks and gluons, are locked up super tight inside protons and neutrons. But back then, in that unimaginable heat, they were totally free, just roaming around in this dense, flowing plasma.
Now this plasma, it holds the universe's very first secret. It's the recipe for literally all the matter we see around us today. And, you guessed it, scientists are on a mission to figure it out.
But that brings up a pretty big problem, right? How in the world do you study something that vanished just microseconds after the Big Bang? It's not like you can just go out and scoop some up.
Well, the answer is you build something of a time machine. Over at CERN at the Large Hadron Collider, scientists take these huge lead ions, think of them as the heavy hearts of lead atoms, and they accelerate them to 99.99999% the speed of light. Then they smash them together to recreate for just the tiniest fraction of a second the insane conditions of the early universe. And they basically run two kinds of experiments. On the left, you've got proton-proton collisions. Smashing single protons together gives them a really clean baseline. It's like their control group, you know? It shows how particles act in a simple vacuum. But on the right, that's the main event. Smashing these giant lead nuclei together. That's what creates enough energy to literally melt matter down into that primordial soup, creating a tiny, fleeting droplet of quark-gluon plasma. So once they've made this stuff, how do they actually study it? Well, this is where it gets really cool. Two teams of scientific detectives just published some fascinating complementary clues. First up, we have the CMS collaboration. They went looking for a telltale wake. Their method is seriously ingenious. During the collision, they create a pair of particles. One is a Z-boson. It's neutral and basically acts like a ghost. It just passes right through the plasma without touching anything. That's their clean probe. But its partner, a parton, which is just a quark or a gluon, gets knocked in the opposite direction and has to plow right through the soup. It's kind of like a speedboat cutting through water. The scientists aren't watching the boat itself, they're looking for the wake it leaves behind. And this is what they found. I mean, this quote from their paper is the scientific version of shouting Eureka. They found probe-induced energy depletion, that's the speedboat losing steam, and the resulting response by the QGP medium. That's the wake. They saw the wake. And they found it with a statistical significance of over 3 sigma. Now, in particle physics, that's a big deal. That's the threshold for calling something evidence. It means what they saw wasn't just some random fluke in the data. It's a real physical effect. So what did this wake actually look like? Well, it showed up as a dip in their data. They found a hole, a depleted region, right where the wake was supposed to be. This is just brilliant proof that the parton pushed the plasma out of the way, leaving this void that then refilled. In other words, the Quark-Gluon plasma flows and ripples, just like a liquid. But hold on, that's only half the story. Now we turn to our second team of detectives, the Alice collaboration. They asked a totally different question. Okay, so it's a liquid, but what's inside it? Is it perfectly smooth, or are there little lumps in it? They went searching for a ricochet. Their whole idea was based on something called quasi-particle scattering. The easiest way to picture it is like a cosmic game of pool. If the plasma is full of dense little quasi-particles, sort of like temporary particle-like hotspots, then another particle shooting through should occasionally smack into one and ricochet off at a wide angle. It's the exact same logic Ernest Rutherford used a century ago to discover the atomic nucleus. So the expectation was crystal clear. If these quasi-particles are in there, they should see more particle scattering way out at wide angles. But in this amazing scientific twist, they found the complete opposite. They saw fewer wide-angle scatterings.
The jets of particles traveling through the plasma actually got narrower, more focused. There were no ricochets.
Okay, so what do we make of this? We've got two huge clues that seem to be pointing in totally different directions. On the one hand, we have a flowing liquid that creates a wake. On the other hand, there are apparently no lumps inside it for particles to ricochet off of. How do these two pieces fit together?
Let's just lay it all out here. The CMS experiment asked, how does the plasma respond? And they found that it acts like a collective fluid, creating a wake. Then the Alice experiment asked, do particles scatter off things inside it? And they found no simple ricochets, but instead this totally unexpected jet narrowing.
And here are the actual papers we're talking about, the sources for this whole story. Two incredible pieces of work. The key thing to realize is that they aren't contradicting each other. They're giving us two different but equally important angles on the same mysterious substance.
So when you put these clues together, a much sharper and way more interesting picture of the early universe starts to come into focus, and it's a lot more complex than we first thought.
So here's the bottom line. The Quark-Gluon Plasma absolutely behaves like a collective, flowing liquid. CMS proved that with the wake. But Alice's result shows it doesn't have any hard little billiard balls inside to scatter off of. Instead, it seems like the energy from a particle moving through it gets absorbed smoothly by the whole medium at once. And that's what causes the jet narrowing. It tells us that the collective, fluid-like forces are what really dominate this stuff.
So the big takeaway here is that these findings aren't at odds at all. They are two absolutely essential pieces of the same puzzle. They show us that the universe's first liquid is both perfectly fluid and perfectly smooth. It's a substance that absorbs energy collectively, not through individual violent collisions. And honestly, that's way more complex and way more fascinating than our simple models ever predicted.
And of course, this just leads to the next massive question. If it's not simple billiard ball ricochets, then what other subtle, complex collective forces are at play inside this primordial liquid? That is the brand new mystery that scientists are now racing to solve. And it's taking us even deeper into the heart of our own cosmic origin story.